Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we will continue with the NIJ standard for strap protection. So, we have discussed that there are 3 different levels, level 1, level 2 with 2 different types of striking energy, E1 level and E2 level for different types of protective textiles. Now, in short we can see that in level 1 for low energy level with the penetration less than 7 mm, we need 24 joule energy, and for high penetration level less than equal to 20 mm, we need 36 joule. Similarly, for level 2 33 joule and 50 joule respectively, and for level 3 we need 43 and 65 joules respectively. Next important terms, the parameter is the angle of incidence. Like in ballistic protection we have seen the angle of incidence is in testing is very important. Here also in strap protection angle of incidence is very important standard. For fair strike the angle basically it should be exactly vertical, but the tolerance is plus minus 5 degree. So, if it is within the plus minus 5 degree, then we will call it as fair strike. Here line of flight of drop mass. Okay. Now, if it strikes at this point exactly where this is a tangent is exactly horizontal, at this point O, this is the point O where the tangent is exactly horizontal, there we will get the drop incidence angle of incidence exactly 90 degree. But to simulate the body curvature, so we can have some curved surface. So, this is the knife blade, and here it is a perpendicular to the tangent. This point is that the point of impact. Now, here we are drawing a tangent on the surface, tangent to the point of impact. At that impact we are drawing tangent, and then we are drawing a perpendicular angle. So, this angle of incidence is a this is called 5 degree deflection. Here it will be as it is 90 degree. So, here angle of incidence will be 0 degree. So, deviation from the perpendicular area angle. So, typically it is the deviation should be maximum 5 degree. So, this is the point of impact, and here is the armors, that is specimen. If it is more than 5 degree, then this will not be called as this your fair strike. That means, in this curved path, if we use this, if we use this point as a, this is the point at the edge, this is the point of impact. In that case, the angle will be little bit higher, and in that case if we draw the perpendicular from this, this angle will be more than 5 degree, which is not recommended, that will not be fair strike. So, for fair strike we have to have a within a certain limit within the perpendicular structure, perpendicular surface, sorry, on the curved surface. Now, composite backing material. So, there are standard composite backing material as per the NIJ standard. So, that contains 3 different types of materials. One is neoprene sponge, which will be at the top, then polyethylene foam will be there in the second layer, and in the last layer there will be rubber. And again the standard is the neoprene sponge will not be a single layer, there will be 4 layers, 1, 2, 3, 4 layers of neoprene sponge will be there. Polyethylene foam will be one layer, single layer, and there will be 2 layers of rubber. So, this is the standard composite backing material, and then so you can see a slab of materials where the samples will be placed. So, samples are placed over this is the backing material, this is the sample. Testing specimen will be placed on the top of the neoprene layer. So, this is the at the top layer of the over the top layer of the neoprene sponge, the specimen will be placed. So, this can be used for flat and flexible armor. So, for any flat armor we can place here, or even for flexible armor we can place this flat one. For carved or female armor we need a carved surface. So, for carved say rigid armor, so we need a carved surface, and the backing material female armor, this type of backing material may not be useful. So, this is only for flat material. For female armor or carved armor, so we need different types of, or we have to change the backing material, which will be as compatible with this carved structure. So, composite, these dimensions are, these are the 4 layers, and polyethylene foam, its density is standard. So, 33 kg per cubic meter foam is used, then rubber. So, length is specified as 381 millimeter and width is 305 millimeter, and here the 4 layers of neoprene sponge are used. Each layer will have 5.8 millimeter width, that height will be that, height will be 5.8 millimeter, thickness will be there, and such 4 layers, and neoprene rubber will be 31 millimeter thickness, and the neoprene foam will be 31 and the rubber will be 6.8 millimeter with the 2 rubber. So, total thickness, if we add all this, then there will be very high thickness. This is the backing material for flat armor, and backing materials for carved armors. For shaped female armor or carved armors, we have to change little bit. So, if armors permit flattening the shape, then it should be flattened and flat materials, that backing materials will be used. So, the armors are the same, even if it is a female body armor. So, if it permits flattening, so we must try to flatten it and use the standard backing material for this for flat materials, flat backing material we can use. First we have to flatten the curved armor, then we use the flat backing material. But if it is not possible, then the backing material should be laid on the carved wooden frame to form the contour which is suitable for, which is actually as per the this carved armor. So, the approaches are two. If the armor is flexible, then we have to make it flatten and use the flattened backing material. If the armor is that the rigid, then we will try to carve the backing material, and still if it is not possible, then neoprene backing material should be cut into the pieces and stacked together inside the armor to get contact of the body armor. So, we will cut into pieces and then stack inside the body armor. So, there are three different approaches are there. Also, there is a witness papers we can place. So, here above the neoprene and below the fabric specimens, we use the witness paper, standard witness paper. So, specimen will be at the top, which will be tested, then the witness paper, then 4 layers of neoprene sponge, then polyethylene foam will be there, single layer, and 2 layers of rubber. So, the function of the witness paper, the single polyart paper is used, which is placed between the specimen and the backing material, and main function is to get possible stab depth or analyze the tip penetration. So, that is important here. We can analyze the tip penetration by knowing this tip geometry. So, there is standard the tip of a knife is used, and suppose this is the witness paper. When the knife penetrates, this will give certain cut, because this knife can easily penetrate through, it will not have any additional protection. So, it will penetrate through that through the back of the specimen, means it will penetrate immediately through this witness paper, and depending on the length cut, we can guess, we can actually calculate the depth of penetration, depth of puncture. So, here suppose this is the length, so L and L, from there if we know the dimension, standard dimension, we can calculate the depth of penetration from this. Okay. And this dimension of the tip are exactly that, these are known dimension. And this witness paper is not used for spike test. this is used for knife test, because knife geometry is known. This is the geometry, and from the length of cut we can calculate the, or we can measure the depth of penetration. But for spike this is not used, because spikes, the diameter of the spike, this total, it is exactly same, it is a cylindrical, but apart from the tip, at the edge there will be tip, but otherwise it is a cylindrical. So, there it is not used, but only for knife we can use this type of witness paper, and this is used for to get the stab depth. So, engineered knife and spikes, the dimension, let us see the dimension. So, there will be two types of knife blades, P1 type and S1 type, as we have already mentioned earlier. So, P1 type is basically, its a size is small and it is a thinner, and it has got one cutting edge. So, it is a smaller size, it is a thinner in depth, and cutting edge, there is a only one cutting edge, like this type of cutting edge, this is the cutting edge. And on the other hand, S2, it is a commando like blades or larger knives, it is thicker than P1 and it has got two cutting edge, both side cutting edge. So, this is the cutting edge, here it is a cutting edge. So, we must specify, or we must test by both P1 type knife and PS1 type knife. So, knife blades P1 and S1, now we can see this is the S1 type, where it is a thinner and it is a smaller knife with a, this is S1, so it is a thicker, S1 is, this is for thicker knife, larger size knife, and both side edge, both edges are cutting edge, these are the cutting edge, this is the cutting edge. This is the standard knife, and P1 will be, so this is S1, here we can see this is the one edge, it is cutting edge, here this is also cutting edge along with the tip. When it penetrates, during penetration it will keep on cutting both the sides, and here the angle, the tip, the angle is 23° standard angle is there, and all these dimensions are given here. It is 100 millimeter. Similarly, for P1 type, which are thinner, only one side, this is only one side cutting angle, and the dimensions are given. And spikes, here we can see the, this is a chamfer which actually penetrates, and apart from that the diameter are exactly same, that is here penetration, that is why we do not use here this witness paper, but in case of P1 and S1 type, like this is S1 type, here suppose there is a penetration, this is the witness paper, this is the length of the cut, and from this dimension if we know the angle, okay, and from this dimension we can calculate this depth of penetration, depth we can calculate. Similarly, this geometry from the P1 type, this geometry we can if we know the witness paper's length, we can calculate the depth of penetration. So, this is a class of pointed weapon that generally used in assault in the correction environment. Now, fair strike, that means below critical below that there will be a different criteria for fair strikes. So, that strike energy should be within the limit of standard that we have already specified. So, there are different types of strike energy E1 level, E2 level. So, within that limit if the strike energy is there, then only we will call it as the fair strike. And the strike should not be, the distance between two strikes should not be less than 51 millimeter from the edge of the sample. So, if the sample is there, the strike should be at least 51, it should be more than 51 millimeter. Okay. From the edge, and the distance between two strikes. Okay. So, and it also should not be less than 51 millimeter from the edge of the backing material also, not from the armor or also not from the edge of the backing material. And distance between two subsequent consecutive strikes, it should be more than 51 millimeter. Okay. These are the basically fair strikes characteristics, and fifth one is that angle of incidence that we have discussed. It should be within plus minus 5 degree. Okay. If we get all this criteria satisfied, then we will take the result as a valid result, otherwise we have to do retest. And drop tower test series, it is used for stab resistance. So, following the fair strike protocol using all 5 guidelines, 5 points that we have discussed earlier, these 5 criteria. So, testing for stab will be done with the using the following table. So, these are the different testing we have to do. So, angle of inclination and thread level we have to use, blade we have to use this type of, and energy level. So, test number is the angle of incidence 0 degree, and for thread level P1, energy level E1, for blade P1. So, we can use blade S1, for that energy level E1, E2 we can use, and blade P1 energy level E1, and for pointed one. So, non flat the S1 and E1, that blade level we can use, thread blade. So, this is for 45 degree maximum angle of incidence will be for non-flat sample. So, these are the for spikes. Spikes again energy level E1, E2 are used for 0 degree angle for flat and non-flat for 45. So, this all these protocols are followed during the strike. Now, how to measure the penetration? First is that there is a fair hit or strike protocol we are using. If the test passes the fair hit or strike protocol, first we have to see that all the previous protocols are followed. Then we will take that the test as a correct test, and then the penetration depths should be measured and tabulated in the record. So, here the main idea is to measure the penetration depth. After testing fair hit, carefully separate the armor from the backing material. So, there will be backing materials are there. So, armors are there. So, we have to separate this material from the backing material. Then we have to observe the spike or blade penetration to the rear side of the armor. So, this is the armor, we are observing the penetration or the blade penetration or spike penetration. If there is a penetration, so if penetration is there or not, that we can first get it from the body armor. So, armor's back side, if there is any hole, then we will consider that there is a penetration. Then the next stage is that if the armor, so design of armor allows, the depth of penetration can be measured directly with the help of the millimeter scale. So, design of armor allows means that if the body armor is a rigid one, okay, or some coating is there. So, that after the knife is taken out, there should not be any relaxation. So, if it is this penetration is there and if it is rigid, then we can directly measure the length of cut, and from there we can measure the depth of penetration. So, it will be the penetration length of the blade or spike at the rear side of the fabric. So, that what we will do, this is the fabric side view, and if the blade penetrates, this is the blade and which penetrates here. So, this depth we are trying to measure, this is the depth of penetration P. So, this we are trying to measure here. So, this is the blade which has penetrated through the armor. So, rear side of the fabric which we are trying to measure. If the rear part of the armor fabric is compressible, so if it is rigid, then it is very simple, we can directly measure with the millimeter scale. But if there is, it is flexible, if it comes back, that is after resilient and if it is compressible, then witness paper is used. So, witness paper will be there will be punch in the witness paper, and that witness paper data we should use the length of cut. Otherwise, there will be if it the compressible material, it will come back to its own shape and the result will be misleading. So, after suppose it is a compressible. So, actual length of cut is this one, but after the armor is taken out, that armor after the knife is taken out, it will reduce the cut length. So, that will give the misleading information. In this case, the spike one will be usable. For spike, a direct measurement with a millimeter scale is suggested. So, if in the witness paper we can directly measure the width of the strike or width of the penetration, that we can measure. Now, from the this is the for rigid material or incompressible material, either we can get this length of cut, or from the witness paper, if it is for compressible material, we will get the length of the cut. So, cut length, and there is a conversion table for both P1 knife and P2 knife. Depending on their structure, we can calculate we can get this depth of penetration. This is the P1 type. So, here if we want to get the depth of penetration, this, and in witness paper we will get this length. This is the length of cut. Length of cut we get from this witness paper, and the depth of penetration we will get from this length of cut, because our the geometry of this knife is known. So, from there we can calculate, and the conversion table is there. This is the conversion table. The length of cut we get from either from the stiff material which is not compressible. This picture is for the incompressible rigid material. Okay. This is a coated material where we can directly get the length. So, this length if we can measure with the help of any scale, and accordingly for P1 type we can get the depth of penetration. So, it is given here. So, if the length is 0.42, then depth of penetration will be 1 millimeter. If it is say 4.77, depth of penetration will be 11. What does it mean? That means, if the depth of penetration is say 5 millimeter, this is a 5 millimeter depth of penetration. For that, the cut length, so 5 millimeter, it will be 2.16. So, for 2.16 millimeter, this is the cut length will be there. So, here it is just reversed. We will first measure the cut length, that is a 2.16 millimeter, and then we will convert it to the depth. So, these are the different length we can measure. From there depth of penetration is calculated. So, here as per the standard, this we should have below 20 millimeter, but effectively we can measure the depth up to 50 millimeter. So, here, so if it is a 20 millimeter, so if the width is more than 12, sorry, this is the length. So, if the length is here more than 8.52 millimeter, then length of cut, then it fails, or less than 7 millimeter depth as per the NIJ standard. Similarly, for S1 type knife, this is the S1 type knife. So, where the depth chart is this is a different from P1 type. So, accordingly we can calculate. So, from the witness paper. So, S1 blade penetration depth from the witness paper cut length for 0 angle of incidence. Again, angle of incidence is also important. So, this is for this data is for 0 angle of incidence, and earlier also you can see for P1 this is again it is for 0 angle of incidence, but if the angle of incidence is different, then there will be different tables available. So, we can calculate the depth of penetration and pass fail criteria here. So, at any angle of incidence like 0 degree or 45 degree angle, the blade or spike should not penetrate greater than 7 millimeter, okay, for any fair strike for E1 strike energies, and for E2 strike energy, higher energy at 0 degree incidence, for blade or spike it should not penetrate more than 20 millimeter. The armor fails the stab resistant drop test if the strike energy is less than E1 penetration, when penetration is more than 7 mm, because it will, despite it is a fair strike. A strike with acceptable penetration under the acceptable condition is fair. There will be more stringent conditions only to strike that are too close to the armor edge or too close to the prior strike, have too much striking energy or any combination of them. So, more stringent conditions, if there is the more stringent condition, then we can use. So, if the more stringent conditions they apply only to strikes are too close to the armor edge. So, this also can be used. Now, the stab resistance test is there, the drop tower assembly, this is a drop tower assembly. This one is a crosshead impactor, and here is a sensor attachment, and at the edge it is a blade attachment. Blades are replaceable after each strike, we have to replace the blade or spikes. Now, here it is a sample holder at the bottom, this is a sample holder. The clamping device, and here this is the standard backing material which we have already discussed. This backing material consists of different layers. So, as per the ASTM standard, 4 layers of neoprene sponge that we have discussed, 1 layer of polyethylene foam and 2 layers of rubber. So, these standard backing materials are used. Now, there is a we have done the test in the lab. You can see here the lab is started, experiment is now there is a strike. The material was there, then after the fair strike, the energy absorption, all this are calculated. So, that is measured. So, we can calculate measure the how much energy is absorbed, what is the stabbing force, everything is calculated along with the this the penetration, depth of penetration. You can see once again there is a suddenly its data is recorded and saved in the system. And apart from the drop test, the fabric strength is measured, tear tensile and tear strength. So, you can see this is the tensile strength, like strip test or grab test are measured. Tear strength is also measured, and where we use the trapezoidal tear strength. So, these are the tests. So, integrity under stress, that we must know before we use for any body armor. Now, there are various innovations and challenges in stab resistance test fabric. The primary challenge remains to create a soft body armor. So, we can have a very thick rigid material, but that will not be helpful as a body armor. So, we have to create the soft body armor, which we have initially preliminary discussed that we can use the shear thickening fluid. So, that soft body armor provides maximum protection while offering comfort and mobility of standard clothing. So, the one way is the fluid integration. So, perfecting the integration of shear thickening fluid for adaptive protection that remains flexible until the impact. So, that material, the whatever body armor, that will remain flexible, okay, till there is a strike. So, if there is an impact, that it will work like a act like a solid. And drapable composites, developing new lightweight multilayer composite that can be molded and draped naturally over the body contour. So, drapable lightweight composites are also used, and to improve the wearer comfort. So, which prioritize the breathability and which will reduce the thermal resistance. So, which will improve the overall comfort and acceptability of the protective gear. The first is that fluid integration. So, for fluid integration we use the shear thickening fluid, it is very commonly used to improve the stab resistance performance. So, it is a non-Newtonian fluid. So, this non-Newtonian fluid is actually unlike water or oil, STF does not follow the Newton's law like in Newton's law, if the shear strain increases and shear stress, so they follow the straight line. So, this is here it does not follow the straight line, its viscosity is not constant and changes with the applied stress. So, that at the shear rate increases, the viscosity increases. So, under low shear rate it flows like a fluid, that is it will be shear thinning, it will be normally there is it will be a fluid, but when the it struck or its shear rate is very high, instantaneously it becomes hard, behaves like a solid, and that effectively gives the protection from the bullet impact, protection from stab. So, this approach is very effective in reducing the weight. So, you can see the viscosity and shear rate here. So, shear rate, so this is the shear stress increases and you can see that viscosity reduces, this is shear thinning, and as shear stress increases, the shear stress also increases, shear rate, shear strain we can call it, shear strain increases, shear stress also increases, but the path of the shear stress increase is different from the shear thinning liquid, shear thinning material, shear thinning. So, shear thickening here the viscosity immediately increases with the increase in shear rate. So, that actually helps in solidifying works that is increase in viscosity that results in that material behaves like a solid. So, the region 1 is slight thinning at very low rate. So, there will be slight thinning, low rate of, and when the rate increases, that becomes in critical shear rate will be there. At that point suddenly there will be changes in the fluid dynamics, shear rate is increases. So, that fluid dynamics will change, and at beyond that critical shear rate, that discontinuous shear thickening takes place, viscosity spikes, and there will be, it will behave like a solid material. And then reversibility is there, when the viscosity, that shear rate reduces after the spike, after the strike, then the shear rate reduces and the material returns to the liquid state instantly after the stress is removed. So, stress is removed, the material becomes like a solid, like a liquid. So, at high shear rate instantaneously it will become, it will behave like a solid, but as soon as the shear stress is relaxed, then it will behave like a liquid. The mechanism is hydrocluster theory is there. So, particle jamming will take place. At rest, the nanoparticles in shear thickening fluid repels each other. So, these particles will repel each other, they will have the same charge, they will repel each other and allows the flow of the fluid. Okay, this will like a fluid it will act. But when we start shearing, when we have high shear rate, so under impact, when we have impact, the hydrodynamic force overcome this repulsion. So, if we are sudden impact is there, there is a repulsion, the hydrodynamic force, this will overcome this repulsive force, and this order disorder transition. So, particles are forced into transient cluster formation. These particles are in cluster formation, and hydrocluster forms, that is this cluster jam together and create temporary solid lattice that resist the flow and that resist the material. Okay. Now, this is the fume silica, and here there is a nanotube we can use. So, for both the cases we can get the cluster formation, and this solidification will help in any protection from the stab or any impact. So, the main materials are that silica nanoparticles are there, typically fumed silica, approximately the size is 100 to 500 nanometer in diameter. These are hard spherical particles. Carrier fluids in shear thickening fluid is the polyethylene glycol, because it is suitable because of its, these are stable non volatile polymer liquid. Molecular weight is PG 200 to 400. And for this we need a solvent, ethanol. This solvent is used as a temporary solvent to lower the viscosity during the fabric impregnation, and after impregnating this will get evaporated, solvent gets evaporated, effectively the dispersed phase silica nanoparticle will remain with the polyethylene glycol on the fabric surface, and then when the impact is there, the silica nanoparticles will get agglomerated and they will form the hard, that they will be effective for the increase in the viscosity, hard layer, it will act as a hard layer. The chemical structure is that silica particles provide a rigid backbone here, and then polyethylene glycol. So, this chain acts as a lubricating medium for the silica nanoparticles. The ether oxygen oxygen atoms in the polyethylene glycol backbone can accept the hydrogen bond from the silica nanoparticle, preventing the particle agglomeration at the rest. So, that is important. So, here the PEG contains actually forms the hydrogen bond with the silica nanoparticle, and in normal condition, in rest condition, they do not get agglomerated. They normally they do not get agglomerated, but they get cluster formation at the high rate, overcoming the repulsive forces. Now, there are some relationship here for shear thickening fluid. The empirical relationship describe the behavior of non-Newtonian fluid. So, tau equal to k gamma power n, that is this is a shear stress in Pascal tau, shear stress and flow consistency index k, and this is the shear rate, and n actually flow behavior index. For Newtonian flow, n equal to 1. Okay. So, and for non-Newtonian flow, so that is for STF, n value is more than 1. So, for shear stress and shear strain, we can get this plot. So, after this understanding this shear thickening fluid, now how to apply on fabric. So, fabrication process is there. So, dispersion we make, the silica is dispersed in polyethylene glycol, okay, using ultrasonication to break the agglomeration. So, what we do? We do ultrasonication and it will prevent agglomeration. Then we dilute this by using the volatile ethanol to reduce the viscosity for soaking. So, we need certain fluidity, that is we reduced viscosity, low viscosity, because we have to soak the material, and this ethanol will get evaporated. This is after the application. Then we have to impregnate the fabric on this dilute solution. So, fabric layers are soaked in the solution for complete saturation, and after that we have to take the fabric, that soaked fabric, and we may use the padding mangle to remove the additional the solution, and then ethanol is evaporated at 60 to 80 degree Celsius, leaving the STF embedded in the fiber. So, STF along with the polyethylene glycol, that will be embedded within the fiber itself. So, if we see the microstructure here, so this is the individual fiber, this individual fiber without any STF, and here if you see B is the fiber without any STF impregnation, and here if you see there is a impregnation is there, and this coating acts as a friction enhancer, which is also important. So, if we use the STF coating on the individual fiber, that will increase the friction between the fiber. So, that will enhance the yarn pull out resistance, so which is very important for stab resistance testing or maybe for bulletproof test vest. So, unlike knit fabric means fabric without any treatment. When the in knit fabric, the yarns can easily slip past the fabric, and which will actually allow the tip to penetrate easily, but in STF coated yarn locks together under impact. So, it is actually acting in both ways. One is it is becoming solidified and that will resist the impact energy. At the same time the yarns become locked. So, when due to the higher friction it become locked, and at that time when the penetration is there, then it will take more and more fibers come together to absorb the penetration energy. So, there are mechanisms of protections. So, yarn pull out and friction. So, these mechanisms we will discuss in the next session. Till then, thank you.